Good morning, everyone. I'd like to cover a little bit of theory today that we kind of rushed on Tuesday, so you could finish your homework. But hopefully today we'll finish with all the concepts that you need for the exam. It's not a lot more. It's mostly about the triaxial test and what is the failure angle, and also about the Mohr circle. First of all, let me come back here a few pages, and I started drawing Mohr circles, and I have forgotten that I didn't talk about Mohr circles. Probably Mohr circles are something that you know from your solids class, and you do remember Mohr circles, right, from the solids class. But I don't know if you remember them well. I probably, it depends how you saw those, if you remember those, what they actually mean or not. And they are very important. We're going to work with Mohr circles a lot. Actually, after this week, next week, we're going to start talking about faults. And when we talk about faults, you will see that the Mohr circles are very important. And we're also going to talk about 3D Mohr circles. So it's going to get one step further into the complexity of what we are trying to understand with the Mohr circle. But the Mohr circle is a very simple concept, okay? Here, as you can see, I have a Mohr circle, and let me explain what that Mohr circle is. If you have an axis where this is shear stress and this is normal stress, a Mohr circle is going to be a representation of all the state of stresses possible for a given state of stress. So for example, if I had a solid that it is subjected to an effective principal stress sigma 1 in one direction and sigma 3 in the other direction, the Mohr circle is going to allow me to plot that state of stress. So how do we go with the Mohr circle? What we do is we plot the principal stresses on the x-axis. So notice that here in the x-axis we have normal stress, right? And if these are principal stresses, by definition, there are no shear stresses on the faces of that solid. And also, we have a convention by which we call sigma 1 the maximum principal stress and sigma 3 the minimum principal stress. If there is no shear stress, notice that this is a shear axis. If there is no shear stress, that means that sigma 3 is going to be somewhere over there, and sigma 1 is going to be somewhere over here. Those are the values of normal stress and the principal stresses on those faces, sigma 1 and sigma 3. Well, the Mohr circle, it's a graphical representation of the state of stress. You remember that we discussed that this state of stress is now sigma 1 and sigma 3 just in this orientation, but if I were to take another coordinate system, I would have normal stresses and shear stresses. And it will be still the same. It's the same state of stress. It just depends in which direction you're looking at. And now we're looking at this in this direction or with this coordinate system, which is aligned with the principal stresses. But if you were to look at this in another coordinate system or in another direction, you will have a normal stress and a shear stress. And that's exactly what the Mohr circle is. I like to draw Mohr circles by always finding here what is the center. In 2 dimensions, the center of the Mohr circle is going to be sigma 1 plus sigma 3 divided by 2. And since this is the center of the Mohr circle, this is going to be a perfect circle. And just for convenience, because it just looks the same, I'm not going to draw the entire circle, but I'm just going to draw half circle. And if I'm drawing a half circle, the radius is going to have that height, more or less.
For the center, don't you have to do sigma 3?
Yes. So
After that, add sigma 3 so that it's like, because like if right that, if you move that percent,
very well, very well. I forgot about that. So the center, the coordinate is at sigma 3 plus the radius of the circle. No, wait. That was fine. That was fine. So the average sigma 1 plus sigma 3 is just the center, okay?
Yeah.
Which you could also write sigma 3 plus the radius. It's the same thing. But let's just keep it like this. This is the average, okay? And now I draw the Mohr circle, okay? So my tips for drawing a circle in paper, which is not, sometimes it's a little bit hard. Remember that the radius has to be the same in all directions, so it's going to be something like this, something like that, and then you draw your circle. It has to be tangent to those points, and it's going to look something like this. So that line is a representation of all the possible state of stresses in a given direction. And let me explain what that is. So let's say that we're looking here at phase number 1. What is the normal stress in this phase? Sigma 1. What is the shear stress? 0. That point over there, right? I'm going to rotate here from this plane 90 degrees, okay? So this goes from here. Imagine this is a plane that rotates 90 degrees up to here. What is the normal stress in this plane? Sigma 3, right? And what is the shear stress? No, the shear. The shear stress in this plane? No, I'm looking at the plane here.
There's no shear stress?
No shear stress. There is just normal stress. Right here there is just normal stress, and here there is just normal stress. Sigma 1 and sigma 3, let me add this just to make it clear, are principal stresses. So they do not have a shear stress. So here is that point. I rotate 90 degrees and I get to this phase, and it's that point over there. So everything in between, actually all those points, are a representation of normal and shear stress of all these planes, from here to there. And notice that to get from here to there, I move 90 degrees over here, but to go from here to there, I move 180 degrees. So if I wanted to measure what is the stress at, say, an angle beta from this other plane, over here I'm going to have to go 2 times beta. And when I get to that point over there is going to tell me what is the normal stress and the shear stress on that plane. So on that plane over here now, if I wanted to measure what is the normal stress and shear stress on that plane, I will be able to do it with the Mohr circle. This is going to be, well, it's actually going in the other direction. Let me change the arrow. No, it's okay. It's okay. This is going like this. This is going to be tau, and this is going to be sigma n. So sigma n is a normal stress, tau is a shear stress. Can you see that if, imagine that for a moment that this plane is actually a fracture and it's cut, it's already broken. So this face will go down and this one will go up. So stress, shear stress will be one down, one up, like that. So if for any given plane, I want to compute what is that normal and shear stress, I can use the Mohr circle. It's just a trigonometry. So the center of the circle is right here, is the average of the two stresses. The radius of the circle is the difference between these two divided by 2. And if I use these two quantities, I can write what is the normal stress. The normal stress is going to be equal to the center of the circle plus cosine, let me add first the radius, plus the radius times cosine of 2 times beta, and the shear stress is going to be the radius of the circle times sine of 2 times beta. Can you see why this is like that? So this cosine. So this cosine is, imagine for a moment that the beta is equal to 45 degrees. So if beta is equal to 45 degrees, then this line will be pointing exactly up there, right? And what is the cosine of 90 degrees? 0, right? So remember the cosine will be the projection of this line on this side. So if it's like that, it's going to be 0. So sigma n is just going to be at the center right here. And the sine of 90 degrees is going to be 1. So tau is going to be equal to the radius. If you have an angle which is less than 45 and it's somewhere, say, over there, your cosine contribution is positive. So this is going to be your sigma n. And your radius is going to be somewhere over there. If you are above 90 degrees, your cosine is going to be negative. And then you're going to subtract a certain amount to c, and you will end up with a point like this. This is super important for shear strength because rocks, unlike materials like metal, they do not fail due to the maximum shear stress. So now that we know the Mohr circle, what do you think is the plane with the maximum shear stress? At what orientation should I look in this rock to find the maximum shear stress? 45 degrees, right? Why? Why do you say that, Mr. A1?
That's because that would translate to 90 degrees on that plot, and that's where we can visually see that we would have the maximum amount.
That point over there, right? The top or the apex of the circle, that's the point of the maximum shear stress. If we were, for example, dealing with metals, usually with metals, you design them to resist a maximum shear stress. But we're not dealing with metals. We're dealing with rocks. And rocks, as we saw last class, they have frictional strength. And because of that frictional strength, they do not depend, the failure does not depend on the maximum shear stress, but rather on the point of if this is a shear failure, this point over here, this is the point of maximum ratio of shear stress to normal stress. Can you see that? So why is this one the point of maximum shear stress or normal stress? Shear stress divided by normal stress is just the slope of that line. So if I had a point, for example, over here, it has zero stress and it has a huge normal stress. But if I had a point over here, it has a small normal stress, but still has zero shear stress. So those planes, if I were to move them one to the other, very similar to what we discussed for this case, as long as there is a normal stress, and if there is no shear stress, this one is not going to move. Okay? And those points are the same. You need enough shear stress and low enough normal stress for those planes to move and to fail in shear. And because of that, the size of the Mohr circle is going to tell us when we get closer to shear failure. And very important too, this point over here is also telling us the point in which there is a maximum ratio of shear stress to normal stress, and therefore tell us too what is the failure angle. So if you see the failure angle over here, you could do some trigonometry, and if this is the friction angle in which tau, the friction law, is sigma n times the tangent of the friction angle, which gives us a friction coefficient, you will see that also this one here, by trigonometry, is a friction coefficient if I take that point over there. And in that case, the failure angle is going to be, can you tell me what is going to be 2 beta? Can you see it from there? So this angle over here is going to be 90 degrees, right? So that's pi over 2. And this angle is just the angle phi. And therefore from here, the failure angle beta, in which there is the max shear to normal stress, is just this one divided by 2. So pi over 4, I'm just going to write it as degrees. It's 45 degrees plus friction angle divided by 2. You had a question, Ms. Montero.
Well, like you said that these are principal stresses and there's no shear stress. So like, is this Mohr circle like describing the shear stress inside of the?
Yes.
Okay.
Yes, it's describing, we don't have shear stresses on these faces, on the faces of the principal stresses, but inside it, there is actually shear stress. As you start to look at planes with other orientation, you will see that you do have a shear stress. And just give me a sec, I find the pieces of this rock. Okay, here it is. I think this one was something like this. So this same test and the same thing that you did in the laboratory, you can be explained with this rock. You did very similar experiments, and if you notice, all the time you had a very steep angle. So the angle from here to there is that failure angle. This is a shear fracture, and the orientation of that fracture depends on the friction coefficient of the rock, and it's always going to be in steep angle. Remember this very well, because we're going to use it a lot when we look at faults, because actually faults, they follow exactly the same principle. So if you know the friction angle, you know what is going to be the shear fracture orientation. The rock is going to fail always in the plane of the maximum shear to normal stress ratio. And there is one more thing I'd like to say here. So if you look at the, here I drew the angle from here to there, right? But I could have also drawn this angle from here to there, like a line like this. There is no reason for choosing one or the other. And if you look at the rock, actually, this one failed also with those two lines. Because there are two possible solutions for this problem. Also in rocks, we can have two sets of fractures. And those are called conjugate fractures. And we'll talk a little bit more about that when we go to faults. So this is all you need to know about the Mohr circle. How do you draw a Mohr circle? You find the principal stresses, you draw those in the x-axis, you throw a circle in the middle, and that's it. And then you have to know how to compute the stresses at a given orientation. We're going to do a lot more of this when we talk about faults. But for now, I'd like that you just remember what is a failure angle and why it is located there. Okay? It's related to the failure line that we have drawn in there, which depends on the frictional strength of the rock. You got a question, Sky? No? Yeah, Mr. Abe.
Value for that angle?
Yes. So the friction coefficient of rocks, it's typically 30 degrees to 45, 50 degrees. So if you consider those two numbers, the failure angle is going to be from 60 degrees to 75 or so degrees, 72 more or less. But I like that you remember the angle 60 degrees, okay? For a friction coefficient of 30 degrees, 30 divided by 2 is 15, 15 plus 45, that gives you 60, okay? All right, any other question? Let me talk about the triaxial test and about pore pressure, okay? And then we'll go into the homework. It's going to be much easier to explain that once I go through that. Okay, this is a sample that we tested in the laboratory. Can you see? Let me find it. Do you see the failure plane? Can you see that? Can you see there is like a kind of a wedge over here? And if you follow that, probably you cannot see it as well as I do over here. But if you follow that, it goes through there. Something like that. So in 3 dimensions, it ends up being a line similar to what we saw before. This sample was tested in a triaxial machine, and it has a membrane around very similar to the ground coffee that we used before. So let me tell you what was going on in this case. We use triaxial test because we many times want to put fluids inside and test what is the effect of fluids, or say measure permeability under stressed conditions. In order to do that, opposite to what you have done before, but you also will do in the lab, not the coming week, but the week after, you're going to get a sample of rock that you're going to put in what is called 2 end caps that are made of steel, and you're going to put all of that surrounded by a membrane which is flexible, very similar to what I showed over here. So here I'm missing the steel end caps, but we'll go over here. all of that goes inside. We want to apply pressure to this, right? So how would you apply pressure to this, outside pressure to this rock? And any idea how you could do that? I forgot to bring, I have a foam polyester cap that was taken under pressure. And I'll try to bring that next time. But basically what you do is you put this in a pressure vessel. So you get a pressure vessel and you put all of that inside, and usually these pressure vessels, they have a very thick wall. In the lab, the pressure vessel that you're going to use has about 1/2 inch wall. In my lab, we have a pressure vessel which is about 3 inches thick, steel. So you can go to very high pressure. So if you want to increase the pressure in here, you'll have to make a hole somewhere in here and connect this to a pump. And usually in the lab, we use these pumps that are called syringe pumps, which is basically a big and expensive syringe that can deliver pressure. So this one moves up and down, and this filled with fluid can deliver a pressure up to, I think the ones in the lab that you're going to use, up to 3,000 psi. What is the depth for 3,000 psi? Can you tell me more or less? A little bit less. But in the order, of the 7,000, 8,000 feet. So that's a lot of pressure, okay? So be careful with that. So with this type of pipe, you would apply a pressure all around the rock that we call, and it's going to be from all directions, that we call PC, or confining pressure. The next step is to add a stress in the other direction. But before we do that, let's say that this is a dry rock, and you apply a confining pressure from all over the sides. What's going to be the state of stress in this rock? What is going to be S1? What is going to be S3? What is going to be S2?
S3 is confining pressure.
Okay, and what about S1? Okay, so therefore S1 is going to be equal to S3, right? This is what is called an isotropic test. And in an isotropic test, you can you just subject the rock to pressure from all sides. But what we're not going to talk about in isotropic tests, we're going to talk about a triaxial test right now. So, and we're going to add pore pressure to this. So if you want to add pore pressure to this test, the first thing that you'll have to do is you'll have to make a hole somewhere over here, and probably another one somewhere over there that connects the pore space of the rock with the outside and with the inside. And then you get a pipe that goes through here, outside, inside, and you can connect that to another set of syringe pumps. And with what these syringe pumps are going to do is they're going to inject fluids in and out of the sample in order to control the pore pressure and in order to, if you want it, to measure permeability. There is one thing that we're missing, and which is if we really want to apply a triaxial test and we want to fail the rock, we need to add a deviatoric stress. And that deviatoric stress is going to come, and this is what you're going to do in the lab, is going to come from applying a stress that also comes in this direction, and you put sort of a piston here, and I'm doing a schematic of the cell that you're going to use in the laboratory. From which you push. I'm not honoring here the size of this stress, but this one should be bigger than that one, okay? And of course, you don't want that to move in any direction, so you don't want that to go down. So we're going to extend the base of that to somewhere over there. So now you can apply a stress in this direction. You're going to have a pore pressure inside the rock. And this is going to be your minimum total stress. And this one over here is going to be your maximum total stress, S1. And if you apply this one, usually you put this one in the load frame. That's what you're going to do later on. You want to apply a force here with the load frame in the lab. And if you know all of those, then you have all the variables that you need for the triaxial test. So what is going to be the effective stress in this case? Remember that we always analyze shear failure from the point of view of effective stresses. So if this is the minimum principal stress and this is the maximum principal stress at failure, what is going to be sigma 1? Always going to be, remember, effective stress is going to be total stress minus pore pressure, and sigma 3 is going to be S3 minus pore pressure. S3